direct reference to the generative and creative power of natural evolution, simulated evolution has long attracted artists and designers. The first wave of systems using evolutionary computation in generative art and computational creativity were interactive breeders, most often using interactive genetic algorithms. With this approach, the delicate task of defining a fitness function is avoided, and human judgment and preferences serve as a fitness function. As we will see, the interactive genetic algorithm and its many variations are still very popular today. English scientist Richard Dawkins introduced the idea of combining evolutionary techniques and computer graphics to create visual forms in his 1986 book, The Blind Watchmaker: Why the Evidence of Evolution Reveals a Universe Without Design. Dawkins uses the notion of biomorphs in his book as evidence that even simple genetic representations can encode a wide variety of forms. Biomorphs are two-dimensional recursive branching structures made up of straight black lines. The length, position, and angle of each line is defined by a simple genome. A small population is evolved interactively. Each generation is generated by applying a range of mutations to the genome on the individual selected by the user. The user can steer the evolution of biomorphs and produce structures reminiscent of real organisms like insects, bats, or trees. We have added a video of Dawkins himself presenting the system in the resource for this session. Dawkins developed the Blind Watchmaker computer model to prove a point about evolution being capable of making complex structures emerge from a series of random mutations and careful selections. Meanwhile, British visual artist William Latham was developing FormSynth, which is a formal notation to explore the construction of complex three-dimensional forms from simple ones. The language and instructions were manipulated through computers, but the evolution of more complex visual forms was executed manually by Latham, as in this example where Latham derives several forms that evolve from each other. In the late 80s, together with mathematicians and programmer Stephen Todd, Latham automated the rendering using the computer graphics possibilities of the time, and applied the idea of interactive genetic algorithm to the breeding of three-dimensional forms. Mutator is a 1987 interactive genetic algorithm program that evolved three-dimensional forms encoded as equations involving simple primitive forms and various geometric transformations and filters. Latham himself was the main user of the system, and the result is a bestiary of three-dimensional forms reminiscent of seashells and aquatic creatures. This model became known as expression-based interactive evolution. In 1991, Carl Sims introduced expression-based interactive evolution more formally with his publications and deployed it in many contexts. The piece Genetic Images from 1991 was an installation consisting of 16 video screens that exhibited 16 different individuals or images. Viewers chose the images to survive to the next generation by standing on sensors in front of them. The pictures that did not survive were replaced by offsprings from the surviving images. The offsprings were produced by combining the characteristics of their parents using genetic operators. Starting from a simple planar image, users could steer the evolution toward a wide variety of images, reflecting a diverse range of aesthetic choices. It is interesting to note that in this piece, it was the audience who got to steer the evolution, and not the artist. The piece was ambitious for the time and ran on a supercomputer called the Connection Machine. This custom-built machine contained more than 32,000 processors. Sims also evolved images himself, like these renderings from 1991. Sims said about the system, "We have difficulty believing that we ourselves were not designed by a god, but arose by accident via natural evolution. Similarly, we may also find it difficult to believe that artificial evolution can compete with our design abilities and perhaps even surpass them." The interactive genetic algorithm proposes a new kind of practice in visual art and more generally in generative art and computational creativity. It integrates computer-assisted creativity and relies on preferences and iteration as opposed to clearly defined goals. Many have taken the path opened by Sims and Latham, and evolutionary art and design have grown into a substantial domain and community. There are an infinite numbers of possible variations and specializations of the general idea of evolutionary computation and its various ingredients. Stephen Rook, for example, added fractals to the set of primitives that can be used and mutated by the system. Rook has a personal aesthetic of landscape-like creations, like in these pieces from 1997 and 1998. For over a decade, Japanese researcher and artist Tatsuo Unemi has used his SBART software, originally released in 1994, to produce a wide variety of expressive renderings, all manually evolved. The system is still available online. By having some parameters in the image being dependent on time, Unemi is capable of generating animations too. Interactive genetic algorithms have been criticized for giving only a very partial and indirect control to the artist or user through the evolution. Some artists find this lack of control frustrating. Some, like David Hart, are still perfecting the technique and finding ways to gain increased control over the colors and forms, like in these pieces evolved in 2007. These examples are only a small sample. If we consider artistic, research, and commercial systems using interactive genetic algorithms, there are simply too many for us to cover here. An interesting development of interactive genetic algorithm is collaborative evolution. As soon as networking technology allowed it, artificial evolution software was made accessible online, allowing individuals, or maybe even more surprisingly, groups of people, to breed 2- or 3-dimensional images and forms together. The original example of this was a system by John Mount, Scott Neil Reilly, and Michael Whitbrook, named International Genetic Art 2. The system ran from 1994 for more than a decade until 2011. It allowed users to rate a number of generated images. Once the user validated their vote, the next generation was produced using the scores assigned by the users together as fitness measure. A good and well-documented example of online collaborative interactive evolution is the 2001 piece Electric Sheep by Scott Draves, a computer scientist who became an artist. The title of the piece is a clever allusion to the Philip K. Dick novel Do Androids Dream of Electric Sheep, which served as the basis for the film Blade Runner. It presents itself as a screensaver application that is available for PC, Mac, Android, and iPad. When these computers sleep, the Electric Sheep software comes alive and the computer communicates with each other over the internet to share the work of creating abstract animations known as sheep through computational evolution. It would take hundreds of years to render the animated version called Dreams in High Fidelity on a single personal computer. So the piece really takes advantage of the distributed nature of the internet. Technically, each electric sheep image is a solution of fixed point to an iterative equation. In other words, the system is breeding fractal-like equations. Draves created a class of fractals called fractal flames. They exploit nonlinear and linear functions composed in additive ways with weights. The equation is solved for each point in the space, and the third dimension is used to look up a color in a palette. A variety of palettes are extracted from existing images or paintings. The electric sheep system is more sophisticated than the usual fractals visualization. The system is parameterized for animation, and the palette is also part of the genome, so it can be bred as well. Even though sheep are actually two-dimensional, a lot of them look three-dimensional. This is due to a tone map that represents how many particles are located within a given pixel. The pixels that are more densely populated mimic occlusion of the ones next to them. So the weights of each pixel is changing over time, which generates the illusion of depth in the animation. Each sheep is a short animation. The system creates smooth transitions between sheep by interpolating between their parameters. There are a lot more possible transitions between sheep than sheep themselves, so it is generating another layer of diversity. Each sheep is 128 frames long, including the frames shown while morphing to the next ship. This is about 4 to 5 seconds per ship. During that time, while the ship is playing as a screensaver, the user can vote for that particular ship using the keyboard. Ship gets to reproduce with a probability proportional to their cumulative number of votes, but along a logarithmic scale to avoid a particular well-liked ship from taking over. This maintains diversity in the ship population. The most popular ship also lives longer. The standard genetic operators are used. It uses one-point crossover, which we studied together, and random mutation. Then a number of heuristics are added to the simple genetic algorithm to maintain diversity. Interestingly, in 2004, some users wrote a graphical interface to edit an individual ship manually. Users started posting new manually generated ship into the pool. With some sort of irony, Scott Draves calls this intelligent design. Each user-designed chromosome is automatically licensed with a Creative Commons with attribution license, so in a way, the authorship of the chromosome is recognized. The human-designed ship were treated well, and the systems were then successful at demultiplying this ship. At its peak, from 2010 to 2011, the system attracted tens of thousands of users every day. Its expansion was in fact limited by its high need for bandwidth. In the mid-90s, the media and corporate interest for cyberculture was on the rise. Absolute Vodka funded the piece Absolute Kelly for the publication of Kevin Skelly's book Out of Control, which discusses how the algorithm covered in this course will change our relationship with technology and with each other and eventually transform our societies. The subtitle of the book is very telling. It is The New Biology of Machines, Social Systems, and the Economic World. The 1996 piece Absolute Kelly was developed by artificial life veteran Jeffrey Ventrella as an online interactive genetic algorithm-based system. Each design of the famous bottle evolved with this system is the result of many users' decisions. This is playing with the notion of distributed intelligence referenced by Kevin Skelly in his book. In other cases, the system that was deployed online is more open-ended and more generic. A good example is the system Pfeiffer by William Langdon that has been running since 2000. It evolves two-dimensional patterns that are described by L systems. So basically, it allows users to evolve L system grammars. We studied L system grammar already. In Pfeiffer, users can use an interactive interface to select which pattern should reproduce and which should cease to exist. Eventually, users can share their favorite patterns, allowing other users to integrate them into their population. Once again, the crowdsourced human fitness function is enabled by the online deployment of the system. Pig Breeder, from 2007, is a more recent example of collaborative, interactive evolution of two-dimensional genetic art. The images are encoded by a type of neural network called the Compositional Pattern Producing Network, or CPPN. They are evolved using a framework called a Neuroevolution of Augmented Topology, or NEAT, which we will study later on in this course. This web-mediated, crowdsourced human computation benefited from a new tool that facilitates the collective exploration of the search space through the notion of branching. Any user can branch off from any individual previously encountered in the forest of evolutionary trees and take another direction. So we can look at the images evolved by others, but also go back to previous stages of the images and branch off from any state to steer the evolution in a different direction. Here we have a series of examples of highly rated images. We see that some of them are almost figurative. Interactive genetic algorithms have also been used in games. For example, Nintendo Wii Me Creator was introduced in 1997. It allowed users to create a personalized avatar. In addition to the manual composition of the various facial characteristics, an interactive evolutionary algorithm was given as an option to breed an avatar. The user first had to choose from a larger population of faces and then navigated faces related to the one chosen through interactive selection of the parent of the next generation. Once they found a face and were happy with their Me avatar, the user could use that particular avatar in various Nintendo games. On rare occasions, interactive genetic algorithms become the central element of the game. In the 2012 Facebook game Petals, users could evolve their own flowers. They could share their creations and sell seeds for actual money through an in-game marketplace. Players could also 3D print their favorite flower by sending its stereolithography file to an on-demand printing service. Other game elements can be interactively bred. FPS Evolver is a 2015 system that allows the interactive and collective evolution of levels in a first-person shooter game. Aoki and Takaki used an interactive genetic algorithm to build a lighting support systems, comparing user performance in a manual lighting task with user employing an aesthetic selection interface. Here, interactive genetic algorithm is used as a computer-assisted design tool for game elements. We have now seen artists breeding images as their practice, and we have seen other computer-assisted creation tools that allow users or groups of users to interactively breed content. There is plenty of software dedicated to IGA. We mentioned SBART earlier in this session. Other software includes Artmatic, Evoltron, Candid, or Visions of Chaos, to name just a few. Some commercial solutions have been deployed as well. We have added some links to the resource section of this session for those who are interested in exploring more. In conclusion, interactive genetic algorithms do not achieve creative tasks automatically per se, but they empower users to explore the vast space of possible outcomes and the creative space in a more or less principled way. It allows for both some control and direction, as well as some surprise and unexpectedness, or even original developments to occur. In other words, it maintains a good balance between exploitation by allowing users to focus on a particular part of the creative space, and exploration by allowing users to jump to unknown and possibly novel parts of the search space. While the idea is to use human judgment to produce the fitness function of the system, the actual interactive element varies considerably from system to system. We distinguish between three broad types of control. The first family of interaction mechanisms are parent selection mechanisms. In these systems, the users are manually selecting parents for the next generation. In some cases, it is a single parent that can asexually reproduce or be mate with other individuals automatically. In other, two parents, and yet in other cases and systems, an unlimited number of parents can be selected. In some cases, the user can even control how much of each parent is used or which aspect of each parent is used or favored. The user selection can be definitive or just count as a vote in a collective choice or aggregated measure. The second family of interaction mechanism allows users to contribute or influence individual fitness values. The user can be directly asked for actual fitness values and fitness scores of individuals, or be asked to rank individuals instead of rating them. The third type of control involves the user defining the fitness function that will then be applied to individuals. In some cases, the user can specify the fitness function explicitly without judging individuals, but by changing the weights of various dimensions of the fitness or by selecting attributes that are desired. The variety of approaches to the interactive element in IGA is astonishing. More generally, there are a number of advantages to using interactive genetic algorithms. First off, humans are good at exercising judgment, whereas implementing a fitness function is very difficult. This is especially true in creative domains, where implementing fitness function is really not simple. Another advantage of interactive genetic algorithms is that they leave the door open for critics of the idea of using a single automatic fitness function. Because everyone is different, the interactive method can potentially increase diversity. Each person can express themselves through unique fitness choices to breed art or design that fits their own preferences. Interactive genetic algorithms empower users. This is perfect when the user, be they a designer, an artist, or a regular person, knows exactly what she or he wants, but cannot describe it as a fitness function. IGA has the potential to extract or reveal from the users what they really want, whether they can formulate it explicitly or not. Using interactive genetic algorithm has the potential to tap into intuitions and judgments that are not easy to quantify. For all these reasons, and as we will see in the rest of this session, interactive genetic algorithms are one of the main paradigms for computer-assisted creativity and computer-assisted design. Of course, nothing is perfect, and interactive genetic algorithms also have some drawbacks. The main problem is that interactive evolution is typically slow, at least slower than fully automated evolution. The human evaluation is a bottleneck. It is even more slow for time-based media like sound, animation, moving images, or when evolving agent behaviors, because the human has to observe a necessarily restricted numbers of individuals to decide which ones are preferable or more fit, and that takes time. So interactive genetic algorithms are typically limited to small populations. Although there are ways around this that we will not cover in this course, user fatigue is a problem, especially for temporal forms. Another complexity of genetic algorithm in general is that the correlation between individual genes and individual attributes can be far from intuitive. In interactive genetic algorithm, this means that often the user has to understand how the coding works to best guide the evolution. Interactive genetic algorithms allow exploration of the space of possible artifacts or forms by empowering humans to steer the evolutionary process. The human acts as the fitness function, providing the aesthetic judgment that guides the evolution. In a way, the evolutionary dimension is just there as a tool to navigate the space in a more or less structured way. Of course, since it is the bottleneck and the crucial element of the system, it did not take long for generative artists and researchers in computational creativity to desire programming the fitness function. We will study automatic fitness function and the other types of fitness functions in the rest of this session.